Good morning, everyone. Am I audible and can you see the slides? Okay. Okay, fine. So let us continue our discussions on deadlock. So we started with resource allocation graph where processes are denoted by circle and resource types are denoted by the square. Right. Now, whenever there are multiple instances of the same resource type, that will be denoted by the small squares inside it or maybe small circles inside it. So for example, here you can see that the resource type with 4 instances, right? So here you can check it like with 4 instances. Now we need to understand the allocation age and the request age, because this is a graph. As I already mentioned, it is a set of vertices and edges where vertices 2 types, one is processes and one is resource types, and edges again I can say 2 types, and that depends on the direction of the edge that is denoted by the arrow. Okay, so for example, whenever any process requests, remember, so this is a request. So if there is an outgoing arrow from the process, as you can see it here, this is outgoing arrow, right? Then that means process Pi is requesting for the resource type Rj rather. Okay, and whenever any resource is allocated to the process, now see here the arrow direction. So direction is towards the process. Meaning of this is resource Rj is allocated to process Pi. In other words, process Pi holds the resource type Rj. Okay, so that we have discussed. Now we gone through this diagram, and then my question is it a deadlock? And then I mentioned no, it is not deadlock. Right. Remember, you need to understand here the resource type which is R2 is held by which process? So answer to this is it is hold, this resource R2 is actually held by both the process P1 and P2. You may wonder here because we say that like one resource will be held by only one process at a time, but still here 2 processes are there. Reason behind that is the instances. So you need to see here there are 2 instances of resource type R2. One instance is held by P2 and other instance is held by P1. Okay, so this is one of the example of resource allocation graph. Remember, there is no, you can think of this as a cycle. So for example, let me change the color and see, for example, this could be a cycle, right? But like it is from R2 to P1, P1 to R1, R1 to P2. But here the problem is the direction of this arrow. Remember, it is from R2 to P2. So you cannot say this as a cycle, right? So this is wrong thing. Whereas if we move to the next slide, for example, something like this, wherein now check the direction. See, if I start with R2, R2 to P1, P1 to R1, R1 to P2, P2 to R3, to P3, and I'm coming back to R2. I'm just following rules. So there is a kind of circular bit, right? This definitely results in deadlock. Reason is very simple. P1 is waiting for P2 because always go by P2. P2 is waiting for P3 because R3 is held by P3 and P3 is waiting for either P1 or P2 because resource type R2 is held by P1. So this creates kind of a circular wait. So this will result, not a single process will make progress here in this scenario, right? And because this cycle definitely gives hint about the deadlock, right? So this is resource allocation with a deadlock, right? So this is how graphs can be used to demonstrate. Now here, if you see, here also we have kind of, say for example, again if I start with R2, R2 to P1, P1 to R1, to P3 to R2, right? This is a cycle because we are coming back to R2, but remember this is not deadlock. Why this is not deadlock is very simple thing. We have multiple instances here. See, 1 and 2 instances are there, 1 and 2 instances are there, right? And P2 is actually not waiting for anyone. P4 is also not waiting for anyone. So whatever the sufficient resources required in order to make progress by the process P2 and P4, they are already with them. Okay, there is no arrow initiated from P2 to P4 and going to the resource type. That means P2 and P4 is not waiting for any resource. So what will happen? Say for example, if P2 is scheduled, P2 once done will definitely release this resource. Maybe this first instance. Once P2 has finished this instance, maybe that will taken by P1, then P1 will continue, right? Then this will be made available because once P1 is finished, this resource becomes free. Resource type R2, right? And once this is free, maybe P3 can also continue. So this is not deadlock. Similarly, if P4 is scheduled, once P4 is done, P4 will release this resource type. This one, the one of the instance. And once this is released, maybe it will be taken by P3. So P3 will continue. Once P3 is done, maybe this resource is, that is R1, resource type will be released, and then P1 can continue. So even though there is a cycle, we cannot say there is a deadlock. Okay. So the important thing is the basic fact about the resource allocation graph. If graph contains no cycle, if there is no cycle, yes, there is guarantee that there is no deadlock, right? But if graph contains a cycle, then two possibilities are there. If we have single instance, then there is a deadlock. Remember, only one instance is there. Then there is a deadlock. If several instances are there, several instances per resource type, then there is a possibility of deadlock. We cannot say 100%. It will be deadlock. Okay, there is one question I think from previous slide. Let me go back. Aditika, is it related to this slide? Okay. Your question is, can two processes hold one resource? No. Two processes cannot hold the same resource if there is a single instance. But if there are multiple instances, for example, in this diagram, think of resource type R1, it is held by P2 also and held by P3 also. Similarly, look for R2. R2 is held by P1 also and P4 also. So if multiple instances are there, then yes, they can hold. But if there is a single instance, no. One process or single instance resource cannot be held by two processes simultaneously. Okay, it should be one after other. Is it clear? Okay. Now, this is a very simple thing. If there are cycle, if there is no cycle, there is no deadlock. Maybe irrespective of one instance or multiple instances of the same resource type. But if one instance is there and cycle is there, then definitely there is a deadlock. And if several instances are there and the cycle is there, then there could be possibility of deadlock. We cannot say 100% yes, there will be deadlock. No. Okay. So there is just a possibility of system resulting in deadlock state. Now that is the basic thing about deadlock. So what the deadlock is and how it is represented and the way how resource allocation graphs are in place for that purpose. Now next thing is what are different methods to handle the deadlock. So I can say there are three methods. The simplest method is this third one. Ignore the problem, and that is used by most of the operating system. They will pretend like their deadlock will not occur at all in the system. Okay, so they will simply ignore the problem. That's it. And that is the reason most of the time if system is hanged, maybe that happens with most of the operating systems also. Like say for example Windows, and even that is true for Linux and Unix also. Okay, so it is something like a system is not responding at all. It is not making any progress, and only solution in that case is just to forcefully shut down the PC and restart it again. Right. So that is the one of the method of handling deadlock. Okay. So that is used by most of the operating systems. Now coming to the first, these are called as deadlock prevention and avoidance. These methods will ensure that system will never enter a deadlock state. Okay. So with these methods, system will never enter into the deadlock state. That means two algorithms are in this method. One is deadlock prevention and one is deadlock avoidance. One is deadlock prevention and deadlock avoidance. Anyways, we'll see what is deadlock prevention and what is deadlock avoidance. Okay. And second method is allow the system to enter a deadlock. That means don't follow the first method. Allow the system to enter into deadlock and then recover. So that is deadlock recovery algorithms. Okay. So three methods as I mentioned. First method is make sure that you need to ensure that system will never enter a deadlock state. So whenever operating system will try to allocate the resources to the processes, then what will happen is it will allocate resources in such a way that OS will ensure that it won't result in deadlock state. And for that, two algorithms are there: deadlock prevention algorithm, deadlock avoidance algorithm. Okay. Second method of handling deadlock is allow the system into enter a deadlock, and then so that means here again two things are required. One is you need to check if deadlock has occurred or not. Okay, and if deadlock has occurred, start the recovery with deadlock recovery. And third one is simply ignore the problem. Okay, operating system will pretend like deadlock never occur in the system, and they will proceed further. So neither they will try to recover from a deadlock, nor they will try like deadlock won't occur kind of a thing. Okay. So let us start with first algorithm, deadlock prevention. A very simple trick is played in this deadlock prevention. And if we again go back to very first or second slide, I mentioned the sufficient and required conditions for deadlock to occur. I guess we discussed four things. One thing was mutual exclusion. Second thing was hold and wait. Third one is no preemption. And fourth one is circular wait. Right? Now, with deadlock prevention, operating system will try to break one of the conditions out of these four, because if four conditions are there, then and then only the deadlock will occur. So wherever possible, operating system will try to break this. So for example, very first condition we discussed was mutual exclusion. Just before 1-2 minutes, somebody asked the question. I think Aditya asked the question, can two processes hold one resource? Now, I just mentioned no. If there is a single instance, you cannot allocate that resource to more than one process. Now, what happens in case of deadlock prevention is, now this allocation is typically divided in two parts. One is shareable resource and one is non-shareable resource. Now, shareable resource is what? That means that resource can be held by multiple processes simultaneously. And one of the reasons for that is, say, for example, read-only files, or rather in classical problems of IPC, I mentioned reader-writer problem, where one resource can be accessed by multiple readers simultaneously. Reason behind that is we are just reading that, we are not modifying it. So these are typically called as shareable resource, the resource which can be shared between multiple processes without any side effects. So now with deadlock prevention, the answer to Aditya's question is, if the resource is shareable, yes, we can share it. Okay, so for example, if process 1, P1, P2 and P3, assume that there are three processes. P1 is waiting for reading something, P2 is waiting for writing something, and P3 is waiting for reading something, which is also required by P1. Now, with this deadlock prevention, P1 and P3, both will be allowed to share the resource. They can read simultaneously because there is no side effect. So, because of this, what will happen is, now we just break that circular waiting condition. P3 is waiting for P1, right? So let me share the whiteboard and I'll try to draw it. So for example, suppose this is process 1, process 2, and process 3. Don't think this the resource allocation graph, because processes are denoted by circles and not by square or rectangle. So P1, P2 and P3. Three processes are there. Circle part is not available here for annotation, so I'm just going with it. Right. Now, suppose P1 is waiting for the resource held by P2, P2 is waiting for resource held by P3, and P3 is waiting for the resource held by P1. Okay. And the resource could be anything. Say, for example, it is shared memory location, which P2 want to write. P2 want to write to that location, and P1 and P3 want to read it. Right. Now what will happen is, we can directly provide access to both, to P1 also and to P3 also. So definitely we can break this circular wait. Okay. So that is the way of working. Like, for example, if four conditions are required, we can break this mutual exclusion. But remember, if the resource is non-shareable, it cannot be shared, then we cannot work on mutual exclusion. We cannot break this because mutual exclusion must hold for non-shareable resource. Okay, so that is one of the technique under deadlock prevention where we'll try to break the mutual exclusion part. Second one is hold and wait. See, one of the result of hold and wait is circular wait. Okay, so in this, what operating system does is operating system will guarantee that, or rather it will enforce some sort of a protocol where the process must request a resource if and only if it does not hold any other resource. So for example, if I need one resource, I can make a request for that, but I should not hold any other resource for that. And in order to implement this kind of stuff, hold and wait, operating system it requires process to request to be allocated all its resources before it begins execution. So for example, I need 1, 2, 3 resources. Maybe initially I need one, then I do some work, then I need second, then I do some work, then I need third, then I do something, and then later I want to release those resources. This won't be allowed in this case. What happens is, if any process needs 3 resources before it begins its execution, it will try to get all the resources. So if 3 resource types are required, it will request for 1, 2, and 3. And if all 3 are available, then it will start its execution. So this will definitely ensure that hold and wait condition will be broken. Because I am holding nothing, and then I am asking for 3 resources, or 3 resource types rather. Okay, so that is how to try to break this hold and wait condition required for deadlock to occur. Problem with this is low resource utilization. Say for example, I need third resource maybe at the end, and that too for just say 5 milliseconds. Example I am saying. Resource 1 is required at the beginning. After say 10 milliseconds or 20 milliseconds, I need resource 2. So resource 1 and resource 2 I want to utilize for next 50 milliseconds. And resource 3 required maybe at last just for 5 milliseconds. So as I mentioned, 20 milliseconds, 50 milliseconds, and 5 milliseconds. Resource 1, resource 2, resource 3. Okay, so let me draw the same part on the whiteboard. Suppose I want to use resource 1. It is for say for example, let me say 10 milliseconds. Then I'll start execution. Then I need resource 2 something like 50 milliseconds. And then at the end, somewhere here, I need resource 3, and that too just for say, for example, 5 milliseconds only. Right? Now what will happen in this case is you are not allowed to request the resource. So maybe I am requesting resource here, that is resource 1. Here I am requesting resource 2. And here I am requesting, say, for example, resource 3. With whatever the divide solution, what happens is something like this. I'll request for R1, I'll request for R2, and I'll request for R3. It is something like this. And then I'll start executing my code. So you must need to acquire the resources before beginning of execution of that process. Now the problem with this approach is I am using R3 just for last 5 milliseconds, but because I need to acquire that resource at the beginning, this will be unutilized for say for example first 10 and then next 50, total 60 milliseconds. So for first 60 milliseconds, resource type 3, R3, is not at all utilized. Okay, and that is the reason the thing I mentioned here is low resource utilization. That is the problem. Low resource utilization. That is, you know. And another problem is it could result in starvation also. Why? Because unnecessarily we are blocking the resource. If somebody else needs, for example, again, if I go back to the whiteboard, some other process, say for example, needs that resource 3 somewhere here at this position. Okay. Now this process actually don't require the resource during this. If I consider this as a timeline, something like this. This is a timeline where our time starts, like say for example 0, here something like 70, something like this. Okay, maybe at time somewhere around 55, 60, another process needs resource 3. We cannot allocate that. Why? Because resource 3, even though process P1 is not using it, we have allocated it to first one, and that is the reason it results in utilization and may result in starvation problem. Any doubt in this? So deadlock prevention will try to break one of the conditions that are necessary for deadlock to occur. So mutual exclusion, yes, it will mark resources like shareable resource and non-shareable. And these locks are actually called as shared lock and exclusive lock. Shared lock and exclusive lock. Okay. Second thing is, don't allow process to hold some resource and then ask for another resource. No. Whatever resources are required, you must acquire before that process begins. Pradnya Kamble, mute yourself. Okay. So, exclusion, hold on. Let us move to the next slide. No preemption. What I mentioned in no preemption required condition is that the resources should not be taken forcefully. That should be happen voluntarily. Okay. So one of the solution for no preemption is operating system will define some sort of protocol. For example, say this one. If process is holding some resource, say assume that process is holding resource R1 and it is requesting another resource, say for example R2. Okay. If process holding some resource, for example R1, and it needs some another resource, say for example R2, and R2 is allocated to someone else, so this process has to wait. This process has to wait. So one of the solution is, if you cannot get resource right now, say whatever the required resource, then what you can do is all resources currently being held will be released. So for example, for process T1, R1 and R2 is required. Now R1 is available with me, no problem. R2 cannot be allocated because it is already used by someone else. What this process will do is, it will release R1 also. Anyways, if I am not continuing with my execution because R2 is not available, there is no point in holding the R1, something like this. Okay. So the process will release this currently allocated. Right. So it is like voluntarily releasing the resources so that others will continue, and once others will finish, then I'll continue. It is something like that. Okay. Now whatever the resource we just release, they must be added to the required resources. And reason behind that is, say for example, in order to continue execution of process P1, R1 and R2 is required. R1 was already there, but I am not able to get the resource R2, so I released R1. So later on, if I want to continue, I need to ask for R1 and R2 also, because R1, even though I acquired, I have released that, right? So whatever the preempted resource is there, that must be added to the list of resources required for which the process is waiting. So previously process was waiting for just R2, now my process will wait for R1 also, right? And whenever that process gets both whatever the required resources, then it will start execution. So step number 1, step number 2, and step number 3. So step number 1 says that if required resource is not there, if you are holding any resource, release that. Required and preempted, both the resources should be added to list of resources required. So that is step number 2. And step number 3 is when all resources that we have released and required, all the resources are available, then we process start its execution. So here we'll try to break the third condition, like no preemption. Okay. And last one is circular wait. Circular wait, I think I already mentioned, like for example, P1 holds R1 waiting for R2, P2 holds R2 waiting for R1, something like that. Okay. So let me go back here. Something like P1, P2, then R1, R2, and this waiting condition is something like this. Waiting for this, allocated to this, this is allocated to this, and this is waiting for this. The meaning of this is very, very simple actually, because this is process 1 and this is process 2. Okay. Now the problem is both the processes actually require R1, right? Suppose this is R1 and this is R2. Both the processes are actually required R1 and R2 in order to execute. But the problem is R1 is allocated to P1, R2 is allocated to P2, and now both are waiting for other resource. Okay. One of the solution device here is to impose the total ordering of the resource types. Meaning of that is very, very simple. The resource types will be ordered, and if you need the resources, say for example R1 and R2 is required by both, you must request the resources in increasing order of their enumeration. Increasing order. This is important thing. Now meaning of this is something like, if I need resource 1, then resource 5, and say for example resource 3. If any process needs resource 1, 5 and 3, then such a process must request the resources in increasing order. That means first of all it should ask for R1, then for R3, and then for R5. So if same thing happens here in this scenario, what will happen is process 1 will ask for R1. Maybe that was free, so it is allocated. Now process 2 will ask for again R1 first of all, not R2. It will ask for R1. Because R1 is already allocated, process 2 has to wait. Again, if it is turn of process, it will ask for R2. That is free, that will be allocated. Getting it, no? Any doubt in this? Any doubt in this? That is what the total ordering is. Okay. So resources must be requested in increasing order of enumeration is like numbers, I can say. So resource type 1, then 2, then 3, then 4, 5, 6, something like that. So whenever you need, say for example, 3 resources are required, R5, R8 and R1. R5, R8 and R1. Then that process must request the resource in the increasing order. So it will request for R1 first, then R5 and then R8. This ensures that there will not be any circular wait. Okay. But again, problem with this approach is if both the resources require at the same time, it is okay. But maybe at the beginning I need some resource and at the end I need some sort of other resource. In that case, definitely this will create a problem. Because again, it will result in something like kind of a starvation or low resource utilization. Right? So deadlock prevention algorithm will try to break one of the necessary condition required for deadlock to occur. It will start with mutual exclusion, shared locks concept is added, okay, then hold and wait. No, all resources should be requested in advance. No preemption. Here we are actually preempting the resources. So what happens is, if some resource is with me and if I'm asking for some other resource, if that other resource is not available, I'll release whatever the resource hold by me. That is what how no preemption condition will be break. And circular wait condition can be break by totally ordering of all the resource types and asking or requesting for the resources in that order only. So increasing order of enumeration. Any doubt in this? Deadlock prevention. Yes, somebody can put on chat. If you have any question, we'll discuss. Otherwise, we'll move to the next. Now see here one of the deadlock example. What happens here is there are 2 threads. This is thread 1. So let me make use of this. So this is thread 1. Okay. And below is 2. So 2 threads are there. And 2 locks are there actually. Let me select. Okay. So this is one lock, first mutex and second mutex. So it will release the second mutex and then first mutex. It is something like acquire 2 locks, do some work and release both the locks. So lock and unlock library with the thread that is used here. And similar kind of thing is there for another thread, but here the order is different. So acquire second mutex, then first mutex, do some work and release first mutex and second mutex. Now the problem is what happens if, for example, suppose this statement is executed. This statement, this is executed by thread 1 and maybe context switching happens, it is executed by thread 2. So what will happen is, now thread 1 acquire first mutex, thread 2 acquire second mutex. Now thread 1 is waiting for second mutex which is already acquired by another thread. And this thread also cannot continue because it is asking for first mutex which is acquired by thread 1. Now this results in a kind of a circular wait. Okay. Now the solution, as I mentioned, total ordering could be solution in this case. So if 2 locks are required by both the threads, say first mutex and second mutex, and by second thread, first mutex and second mutex. So what will happen is, here in this place, what we get is first mutex. That is already acquired by thread 1. So thread 2 has to wait. Thread 1 will complete and then thread 2 can start. Okay, so this is one of the deadlock example, and that is the reason I mentioned not necessarily all kind of resources or just input output devices, because most of the time I'm giving example of the printer, that is easy to understand. But if mutex locks are also there, that also result in deadlock if not used properly. Now, deadlock example with lock ordering. Now this is also interesting part. Suppose this is the application used in banking, and this one is the account number. So account number from account number 2, and we want to transfer some amount from account from to 2. So maybe 2 locks are required here. So mutex lock 1 and lock 2. So we'll block account from and account 2. So lock 1, lock 2, acquire both the locks. Now because we want to transfer the amount, transferring is what? Withdraw first of all from the account from and deposit into account 2. So if A and B, these are account numbers, withdraw from account A and deposit into account B. That is what the thing is. So first of all, we need to lock the balance of A, also lock the balance of B, so that no changes will happen simultaneously. So I acquired both the locks. So for from and for 2. Okay. Now this is withdraw and this is deposit, and once both are done, you simply release both the locks. Now this logically seems perfect, but then the problem is, for example, if you try 2 transactions concurrently, and these 2 transactions are transfer A to B, account A to account B, some amount. Now that amount is mentioned here, like $25, and second transaction is transfer from B to A. The amount is not important here actually, something like this. Now if these 2 are there, and if we both are calling the same function, something like transaction, now this becomes from, and this account becomes 2, right? So first transaction, it will try to acquire lock on 1, and this lock 1 is what? In first transaction, it may be account A, and for second transaction, it is account B, right? Now if you try to acquire next one, now for first transaction, acquire lock 2 is for B, and for second transaction, acquire lock on 2 account is account A. So this definitely results in some sort of a deadlock, and that is the reason we need to have kind of ordering. So if A and B accounts are there, maybe some sort of order is there. For example, account number, something like 101 and 107. You can imagine that as a ordering. So if you need both, maybe you will acquire on 101 first and then 107, and that protocol has to be followed by both. So even though logically this solution seems very fine, this may result in deadlock. Any doubt in this? Any doubt in this? Is that fine? Anyone? Just have a look at the same code 2 times. Once for transaction A and once for transaction B. Where acquiring lock 1 is like locking account A and acquiring lock 2 is like locking account B. But this exactly get reversed for second transaction, and if both transactions are running concurrently, then definitely this creates a problem. Okay, so let us move to the next. Now, first algorithm is deadlock avoidance. Will try to break one of the conditions, maybe by preemption, maybe with shared lock, maybe with asking for all the resources at the beginning. That is, we'll try to break hold and wait. And last one is by total ordering of resources. Okay. Now let us see the deadlock avoidance algorithm. In order to make use of this deadlock avoidance, there is some prerequisite, and that prerequisite is we need some sort of prior information. Some prior information is required, and this prior information is utilized to see if allocating that resource will result in deadlock or not. Okay, and this prior information is mentioned below. For example, very first part of this is the maximum number of resources of each type required. If process P1 is there and that needs 3 resource types, now how many instances of those 3 types required? That should be known well in advance to this deadlock avoidance algorithm. So that is one thing, the maximum number of resources required. Okay. Now what happens is this deadlock avoidance algorithm dynamically examine the resource allocation state to ensure that there can never be a circular wait condition. That means what happens is whatever number of processes are there, whatever number of resource types are there, operating system, or rather I can say deadlock avoidance algorithm more specifically will try to build the resource allocation graph. So whenever any process Pi requests for resource Rj, it will see that if that age is added into the resource allocation graph, does it results in a cycle? Because if cycle is there, that means there is a deadlock. And if it found cycle there, what this algorithm does is that request is not fulfilled even though that resource is available. So allocating resource, if results in deadlock, do not allocate that resource to that process. That is as simple as that. It will try to break that circular wait condition. Okay, getting it now? So first upon, we need to know what is the need of each and every process well in advance, and then the algorithm will check resource allocation state. Just a minute. Okay. Third thing is the resource allocation number of available and allocated resources and the maximum demand. So how many resources are available, how many resources are allocated, and what is the maximum demand. So how many resources exist, how many resource types are allocated to which processes, what is remaining resources, and what is the maximum demand. All that primary information is required. Now there is a concept of something called as a safe state. Safe. Okay. So when any process requests the available resource, then just this one, let me highlight it, set state. Okay. So when any process requests the available resource, system must decide if immediate allocation leaves the system in set state. That the same thing now it is put in more technical words. Okay. So whenever any process requests for the resource, system will check if immediate allocation of that resource to the process results in system will be in safe state or not. If it results in safe state, that will be allocated. Okay. Now, what is the safe state? First of all, it is the sequence of all the processes. For example, P1, P2 up to Pn. It is if there exists a sequence of all the processes such that for each process the resources that process request can be satisfied by currently available resource plus resources held by all other processes. Meaning of that is very, very simple. Let's say, for example, P1, P2, P3, P4, P5. 5 processes are there. And suppose this is turn of P2 and P2 is requesting some sort of resource. Okay. There should exist one sequence in such a way that we can allocate the requested resource type by P2 if and only if there is a sequence, safe sequence rather, by which all the processes can be satisfied by resources and system won't result in deadlock state. So whatever the currently available resources are there plus resources held by other processes, right? If it satisfies, that means it is safe to allocate the resource required by process 2. Okay. Same thing is elaborated below. For example, if PI request needs are not immediately available, then PI can wait until all PJ have finished. So that means it's very simple. For example, I just give an example of P2. If the requested resource cannot be immediately available for P2, P2 has to wait for others. Okay. But the thing is, there should be at least one sequence. It should not happen like everybody waiting. Okay. So if PI don't find the resource immediately, it has to wait for PJ. When PJ process is finished, now PI can obtain the needed resources and it can execute. Once it executed successfully, it will return all the allocated resources, so all other processes can continue and process PJ will be terminated. When any process PI gets terminated, then PI plus 1, that means other processes can obtain required resources, so on and so forth. So that is how it will continue. So this is called as a safe state. Okay. If system is in safe state, there is no deadlock. If system is in unsafe state, there is a possibility of deadlock. That means there doesn't exist such a sequence of execution of processes. Then we say system is not in safe state, unsafe state. So there is a possibility of deadlock. And the deadlock avoidance algorithm ensures that system will never enter an unsafe state by not allowing the resource, even though it is a free. Even though it is a free. Maybe P2 needs some resource R3, it is available, but if assigning that resource R3 to process 2, it may result in unsafe state. In that case, such resource is not allocated to people. Maybe that is required by somebody else. Okay. That is how same thing is given there. If system is in safe state, there is no deadlock. But if system is unsafe, remember there is a possibility, and that is the reason some part of unsafe is called as a deadlock. Okay. Not everything of unsafe is a deadlock. There is a possibility. Okay. Now for avoidance algorithm, if there is a single instance of resource type, we'll simply make use of resource allocation graph. And if there are multiple instances of resource type, we need to understand the banker's algorithm, which is deadlock avoidance algorithm. That we'll discuss in next lecture. Do you have any doubts?